Hi everyone, welcome back to Chem Help ASAP. In previous videos with Lewis structures, we have always followed the octet rule. Atoms have always had 8 electrons around them. The only exceptions we've talked about are hydrogen and helium. Well, hold on to your hats because today we are going to talk about even more exceptions to the octet rule. So let's start breaking the rules. Even though we are breaking rules today, I still am going to keep our rules for Lewis structures on the page. Okay, let's take a look at our first rule breaker, BF3. So let's add up valence. Boron gives me 3. I have 3 fluorines. They each give me 7. I have 24 valence electrons. Okay, I am going to break the rules myself here, and I am actually going to give you the Lewis structure for this molecule. Now, you will notice something right away. Take a look at the boron in the center. Does it have a complete octet? No, it does not. It actually only has 6 valence electrons. Now, you might be thinking, well, hold on, why don't we just do boron with a double bond to one of the fluorines? But what scientists have found experimentally is that double bond does not exist. Boron actually prefers to have single bonds to fluorine. So this is a case where boron has an incomplete octet. Now we don't see this very often in stable species, but boron and sometimes beryllium will form incomplete octets. So that is our first rule breaker of this video. Let's take a look at another rule breaker. Xenon bonded to 4 fluorine atoms. Okay, if I'm counting up valence, I have 8 from xenon. I have 4 fluorines. They each have 7. I have 36 total valence electrons. I'm going to put xenon in the middle. I'm just doing my Lewis structure just like we always do. I'll start with single bonds. That is 8 electrons. Okay, let me add in lone pairs. And you can see I have a problem. I have satisfied everybody's octet, but I still have 4 valence electrons. What do I do with those leftover valence electrons? Well, what you do with them is you put them on the central atom. So they are going to go on xenon right there. So xenon has 4 bonds and 2 lone pairs. This is called an expanded octet. Now let me draw this with the bonds, and I think you'll see it a little more clearly. Of course, we have to put our lone pairs in. Now, if you need an atom to have an expanded octet, the most important thing is that atom must be able to take extra electrons. So if you are looking at elements in the first or second period, i.e. anything up to neon, it does not have space to take extra electrons. For the first period, it only has the one s orbital, so that's why hydrogen and helium max out at 2 electrons. For the second period, all of those elements only have the 2s and the 2p orbitals. They cannot take more than 8. So you must have an element that is either in the third period or higher to take that expanded octet. Fluorine is in the second period. It cannot take more than 8 electrons. Therefore, those electrons must go on the central atom. As a general rule of thumb, extra lone pairs will go on the central atom. Of course, make sure that that central atom is not in the second period. Now, let's take a look at one more structure. Let's take selenium, and we are actually going to put 6 chlorine atoms around it. Okay, so if I am adding up my valence, selenium gives me 6. I have 6 chlorine atoms. They each have 7 valence electrons. I have 48 valence electrons. You can already tell that selenium is going to have an expanded octet. Now double check, where is selenium on the periodic table? You'll find it at atomic number 34. That means that yes, it is actually in the 4th period. It can take an expanded octet. So I am going to have 6 chlorine atoms around selenium. Now again, make sure that you put in your lone pairs. And again, double check your valence electrons. Have I used 48 valence electrons? You can see that things get a little crowded when you've got 6 atoms around a central atom, don't they? When that happens, just make sure for your reader's sake that you keep those electron pairs very clear so they know where they go.
One thing I want to emphasize again is that your second row or your second period elements will never have an expanded octet. Remember, they don't have access to a d orbital, so they've got no place to put extra electrons. So you will never see like a carbon atom with 5 bonds or say 4 bonds in a lone pair. It simply doesn't have the space. Just like hydrogen and helium can never take more than 1 bond, they only have the 1s orbital. They can't fit any more electrons. However, I hope you found this video helpful, and thanks so much for watching.